Hey guys, let's talk about a different way to use our polar plane. And this other way to use our polar plane is to work with the polar form of complex numbers. Now we know complex numbers, they're of the form a plus bi, where a and b are real numbers, and I is the imaginary number square root of -1. And we have our polar plane. You can work in your polar plane. Or I'm sorry, not our polar plane, our complex plane, where the horizontal axis is A, the vertical axis is B. So if we had, like, let's say we had the number 2 minus 3i, it would be something like this. Where this is 2, and that's -3. So we're defining A and B in terms of rectangular coordinate form, where A is the X and B is the Y. Another way to work with this is treating it not rectangularly, but in terms of polar. So working with an R and a theta. So we could rewrite this using R and theta just like we could rewrite the point 2, -3 in terms of R and theta. So in this case, R, since that's 2 and that's 3, R is the square root of 4 plus 9, so root 13. And theta, tangent of theta, would be 2 pi minus tangent of 2 pi minus theta would be 3 over 2. All right, because 3 over 2 would give you this reference angle, and then we would have 2 pi minus that would give 2 pi minus theta would give us that reference angle. All right, so this would help us get that. So theta equals 2 pi minus tangent inverse of 3/2. So another way to express this, isn't the horizontal just r cosine of theta? And our vertical r sine of theta? So we can rewrite this number as root 13 cosine of, I'm not going to rewrite that value, but cosine of theta plus root 13 sine of theta times I. Most of the time you'll actually write as plus I root 13 sine of theta, just putting the I out front. All right, so this number is the same thing as that number. It's just the polar form, also known as the trigonometric form of that complex number. So they say the same thing. So in general, if a plus bi is a complex number, then it can be written as r times cosine of theta plus I sine of theta. That's our polar or complex form. And in general, every single time, r is going to equal the square root of a squared plus b squared because of the Pythagorean theorem. Theta is going to be tangent inverse of b over a, and you would just figure out what and that would give you the reference angle, and then you would work from there. I just don't feel like writing that out. And likewise, a would always be r cosine of theta, and b would always be r sine of theta. All right. So this is how we can go back and forth between standard complex form and polar form of complex numbers. Now, what the polar form is handy with is doing operations with complex numbers, specifically multiplication and division. If you had, say, a complex number z1 equals r1 cosine of theta 1 plus I sine of theta 1, and then z2 was r2 cosine of theta 2 plus I sine of theta 2. If you want to multiply these two together, the r and the r's would multiply together, r1, r2. But then these binomials we could distribute through. Cosine times cosine, so cosine of theta 1, cosine of theta 2. And then cosine times that I sine. So plus I cosine of theta 1, sine of theta 2. And then I sine times cosine, plus I cosine of theta 2, sine of theta 1. And then I sine times I sine. And we know I times I squared, is -1, so it's -1. I don't know why I wrote the 1, I could have just left it as negative. Sine of theta 1, sine of theta 2. So inside here, we have two values without the I and two values with the I. So I'm going to group the two without the I's together and group the two with the I's together. So without the I's, it's cosine of theta 1, cosine of theta 2, and then minus sine of theta 1, sine of theta 2. That looks pretty familiar. And then the other ones, they both have the I in common, so I'm just going to factor it out. And then we have cosine theta 1, sine of theta 2, plus sine of theta 1, cosine theta 2. Now, wait a minute. These are just some identities that we know. So z1, z2 equals r1, r2. Oops, that was supposed to be a 1. Okay. Cosine theta 1, cosine theta 2 minus sine theta 1, sine theta 2. That's one of our sum and difference identities for cosine, specifically cosine of a sum. Theta 1 plus theta 2. And then plus I. And cosine of one angle times sine of the second angle plus sine of one angle times cosine of the second angle. That's our sine of a sum identity. So this is what you can do anytime you're multiplying two complex numbers in polar form. A very similar derivation would get you how to do it with the quotient. You can do that derivation on your own, but if you have the same z1 and z2, it's going to be r1 over r2, and then cosine of the difference of the angles, plus I sine of the difference of the angles. And of course, z2 can't equal 0. All right, So we've got these two rules. Let's just try an example. Let's say that we had two complex numbers. Let's say z1 was 3 cosine of pi over 4 plus I sine of pi over 4. And z2 was 2 cosine pi over 4 plus I, oh, not pi over 4. I don't want to do the same angle. Let me start that again. 3 cosine pi over 4 plus I sine pi over 4. And then 2 cosine 3 pi over 4 plus I sine of 3 pi over 4. All right. So if we want to multiply these two, z1 times z2, you multiply the r's, 2 times 3 is 6, and then you add the angles. So cosine of pi over 4 plus 3 pi over 4 is pi. So it'd be the same thing here. And we're totally capable of evaluating pi, cosine of pi and sine of pi. Cosine of pi is -1, sine of pi is 0. So it's 6 times -1. It's just -6. And if we want to divide, similarly, z1 over z2, it'll be 3 over 2. And then cosine of the difference of the angles. So pi over 4 minus 3 pi over 4 is -2 pi over 4, which is negative pi over 2, plus I sine of negative pi over 2. So this time, cosine negative pi over 2 is 0. Sine of negative pi over 2 is -1. So it'd be -3/2 I. All right. So multiplying and dividing, it's a little easy. And also raising it to a power. Because raising something to a power is just multiplying it over and over again. So if we had our standard z equals r cosine theta plus I sine of theta, and that's z to the first. If we did the z to the second, that's z times z, so we would use multiplication. So we multiply the radii together, well, r times r is r squared, and then add the angles together, so it'd be theta and theta, so it'd be theta plus theta, so cosine 2 theta plus I sine of 2 theta. If we did z cubed, that's just z times z squared, so it's the product of these two. R times r squared is r cubed. Add the angles. 2 theta and theta is 3 theta. If we had z to the fourth, that's just z times z cubed. So it's this one and that one. R cubed times r is r to the fourth. Add the angles. I hope at this point you're recognizing the pattern that in general, z to the n equals, if our number is z equals r cosine theta I sine of theta, it's r to the n times cosine of n theta plus I sine of n theta. This was founded by a guy named de Moivre, and it's named after him. This is called de Moivre's theorem. All right. Hope that makes sense. I'll talk to you guys later.